So for number 15, you really want to focus on what's happening with that sequence. So a ball bounces from a height of 2 meters and returns to 80% of its previous height on every subsequent bounce. Find the total distance traveled by the ball until it stops bouncing.
That's not possible.
Yeah, it's always going to keep bouncing. But we're going to figure out how to get around this until it stops bouncing business pretty easily. So a ball bounces from a height of 2 meters and returns to 80% of its previous height. So what is A sub 1? What's the first height that we have? Yeah. So A sub 1 is going to be 2. And what's A sub 2? Yeah, whatever 80% of 2 is. 1.6. And what's A sub 3?
1.28.
1.28. Okay. So, now you said something a little bit earlier that was actually really poignant. You said it never stops bouncing. Right? It always just exponentially decays and gets super duper close to the 0 height, but never actually reaches that height. So how are we going to handle this problem? Exactly, make it an infinite sequence or an infinite series here. So we start at 2 meters. Do we know what our R is?
Yeah.
What is our R? 4/5 or 0.8?
Or 8 tenths.
Same thing, 4/5, 8 tenths.
Or 80/100.
So, I know R, I know A sub 1. What's the formula for the sum of an infinite geometric sequence?
N times A1 plus A2 over 2.
A1 over 1 minus R. That's the infinite one. You were talking about the finite.
Yeah. Okay.
Remember, the only one that has an infinite geometric sequence, or a geometric series when you add up all the terms for infinity, is geometric sequences that have an R of what?
Less than 1.
Has to be less than 1. Whether it's positive or negative, it has to be less than 1. So the absolute value has to be less than 1. If R is less than 1. Alright, so the sum of the infinite sequence here is just going to be 2 divided by 0.2. So what's 2 divided by 0.2? So the total distance traveled is 10 meters. Yeah.
Doesn't it always never hit the surface? Because then it goes half of half and half of half and then half of half.
Exactly. It goes half to half to half. It goes half of the 2, half of the 1.6, half of the whatever half of 1.6 is. 0.8. Half of that 0.8, half of the 0.4, half of the 0.2. So it never actually goes to 0.
Not true.
Real world, right? Imagine this. Imagine you take a sheet of paper, right? Take a sheet of paper, cut it in half, cut it in half again, cut it in half again, cut it in half again. Eventually your sheet of paper, right? Take a sheet of paper, cut it in half, take that sheet of paper and cut it in half again. Here, I'll even slice it in half for you. There it is, cut in half once.
That's actually half.
No, you won't.
Cut it in half again. It's only going to bounce real little bit. It's not going to bounce a whole lot. Yeah, it's only, I know, I ran out of English. It's not going to bounce very high. Just like this sheet of paper is never going to be totally gone. It's always just going to have a smaller and smaller piece. But no matter how small that piece is,
Still gonna be there.
it's still.
So if I come back to the bouncy ball like an hour later, it's still bouncing?
Yeah, they're bouncing.
According to the question.
Yeah.
Real life.
Real life, real life, it's
Well, in real life, there's more to the problem than it's never going to bounce back 80% exactly every time, because that's not the way the real world works. It's a very close approximation, but in the real world, you have things that cause the energy in that ball to dissipate. So when you hear a ball bouncing, boom, when you hear that ball bouncing, that's energy being wasted. So it's more of a physics problem than a math problem at that point.
Yeah, gravity. Zero
So,
gravity.
number 16 has a question. Yeah, what's it asking? Yeah. Number 16 just fell down.
I love that.
I'm gonna guess after the end of 10 years,
What do you